Okay, hello. So this is chapter 8 for flood routing. Alright, so for our syllabus, we will learn on reservoir routing and channel routing. So the big question is, what is routing? So in hydrology, routing is a technique used to predict the change in shape of a hydrograph. So here we can see there are two hydrographs. So for example, we have a hydrograph from an upstream. Okay. And then we want to estimate how is the hydrograph at downstream. So basically, this is routing in hydrology. So it predicts the change in shape of a hydrograph as water moves through a river, channel, or a reservoir. Okay, so what is it is used for? In flood forecasting, hydrologists may want to know how a short burst of intense rain in an area upstream of a city, for example, will change as it reaches the city. So more specifically, we can say it as flow routing. So flow routing is a procedure to determine the time and magnitude of flow. So in this case, it's hydrograph at a point on a watercourse from known or assumed hydrographs at one or more points upstream. So this is actually the same with what I mentioned before on what is routing. Okay, so for our syllabus, we in chapter 8 we mention it as flood routing. Okay, so what is the connection here? So from flow routing, so we can actually say it as a flood routing. Okay, if the flow is a flood, okay, the procedure is specifically known as flood routing. In a broad sense, flow routing may be considered as an analysis to trace the flow through a hydrologic system given the input. So in this case, the input is the flow at upstream. Okay? And then so we want to estimate the flow at downstream. So there are some divided methods of flow routing. For example, one is a distributed system model. Okay, so in this case, it is also called a hydraulic routing. Okay, this is because it is calculated as a function of space and time through the system, okay, or along the system. For example, here for hydraulic routing, it uses the continuity equation and equation of motion of unsteady flow. So unsteady flow means that it use the equation which relates the on the hydraulic parameters. For example, the river. So we need to know the river cross section, slope. Okay, so it relates with the unsteady flow. And the other one is a lump system model. Okay, so we also call it as a hydrologic routing. So this is actually calculated as a function of time alone at a particular location. So it only employs the continuity equation. So there's a difference here. For hydraulic routing, it also includes the equation of motion of unsteady flow. But for hydrologic routing, it only considers the continuity equation. Okay, and it's just at a particular location. Okay, compared to a hydraulic routing, is a function of space. Okay, so for our scope, we will look into hydrologic routing. So in a more simple way in explaining the methods of flow routing, so there are two. You may adopt the hydraulic method, hydraulic routing, or the hydrologic routing. Okay, so for our case, we will look into hydrologic routing only. And from here, it employs the continuity equation. Okay, and then there is divided more into two condition. For example, if it's a reservoir, okay, or it's a channel. So a reservoir, for example, a dam or detention pond. So that is a condition of a reservoir. or the other hand is channel routing. It may be a river or an open channel. Okay, so we will look into these two, reservoir routing and channel routing. Okay, so there are methods here. Okay, so here is a summary of the components of flow routing. Okay, again, so hydrologic routing computes outflow hydrograph corresponding to a given inflow hydrograph. Okay, so why what it is used for? So again, it is used for flood forecasting, flood protection, reservoir design, and spillway design. Okay, invariably include this flood routing. So it's actually flow routing, but because the reason it is used for is for flood management, so then we call it flood routing. So if for example, if we have a again, this may be a stream, okay, a flow of water coming from then this direction. So we have, for example, this green color is inflow, okay, inflow cross section or location of observation, and then we want to estimate the hydrograph at this downstream. Okay, so this is downstream, ds. Okay, and the green one is upstream, yeah, up, upstream. Okay, so this arrow is the flow of water. So we have two conditions to apply this hydrologic routing. One is for reservoir routing. Okay, so what does this mean, reservoir routing? Is if we have a reservoir here. For example, the flow coming in to a reservoir, okay, and going out to a reservoir. So we want to know the hydrograph. But we need to know the inflow hydrographers, okay, and then we want to estimate the outflow hydrograph. Okay, so if we have a reservoir, then it is called a reservoir routing. But if we don't have this reservoir, it's just a channel or river or an open channel, then we call it a channel routing. The same concept, we need to know the inflow and we want to estimate the outflow. Okay, but for this case, for reservoir routing, we can use another method, and for channel routing, we use the other different method. So this shows some figures for reservoir, a reservoir, and the reason we do reservoir routing. For example, number one, to design of the capacity of spillways. So where is spillways? So here is spillways. These are all spillways, and the other reservoir outlet structures or others, not just spillways, but there are many more types of reservoir outlet. For example, a pipe, a big pipe. Okay, and this is spillway. And besides that, to determine the location and sizing of the capacity of reservoir, we want to know what is the size of this reservoir. Okay, does the volume will make a difference on the outflow hydrograph. Okay, so that's two reasons. Okay, for channel routing, the keyword is channel. Okay, so it's river. There are no reservoirs. So channel routing is for channel. Okay, so the change, what we want to do is actually to see the change in the shape of hydrograph. So again, we have inflow hydrograph, which is upstream. Okay, let's say there is a flow of river this way. So we have a inflow hydrograph data here. Okay, there is a hydrograph there. So we want to see the change in the shape of hydrograph. Also, what is the shape of the outflow hydrograph here? Okay, will it has a smaller peak, Q peak, or what time it delays? Okay, and then the method can predict the flood hydrograph at various sections. Okay, so for channel routing, we can determine the hydrograph Okay, we can say not just flood hydrograph, we can just see it as hydrograph. So if we have a river, so any point, this point, this point, this point, this point, so we can predict the hydrograph. Okay, and as part of that is useful in flood forecasting operations and flood protection works. Okay, so we can estimate. For example, at here, this area is a city, okay, town, bandar. So we know the inflow hydrograph here. I put inflow hydrograph as I. So we know this I, this hydrograph at the upstream. So we can estimate the hydrograph at the this city. Okay, so then we can know what happened with the Q, whether a higher Q peak, and so will it overflow the channel. So this is the reason for us to doing channel routing. Alright, so we finish part 1, which is on introduction. I hope you understand the basic understanding of flow routing. Okay, what's the difference between reservoir routing and channel routing? Both are flow routing, but the conditions are different. So for part 2, we look into reservoir routing. So how do we calculate this? How do we estimate the outflow of uh, going out from a reservoir, okay, by using information of the inflow of hydrograph coming into the reservoir. So this is part 2 for reservoir routing calculation. Okay, so again we repeat the definition of flow routing. So you should understand because this is the basic understanding. So let's say we have this watershed and this one, let me, yeah. So this one is the inflow, okay, from the upstream, upstream of the reservoir. Okay, so we have a hydrograph here. So for flow routing, we can determine the hydrograph along the channel. Okay, so this is along the channel or river. So we can determine this hydrograph. Okay, and then here. Okay, so what happened here is there will be a as the hydrograph travels, okay, it attenuates or gets delayed. So we can see here the first hydrograph at the upstream, the peak is higher compared to the middle one. Okay, this the lighter orange color here, the peak is lower, and then as it goes down more downstream, the peak is the lowest. So this is what we call attenuates, or and the hydrograph also get delayed. See the time here, it gets delayed. Okay, so this is the basic equation where we used for the reservoir routing. So it is the continuity equation. Okay, why do we call it continuity equation? It's like a time step. At this time and then the next time. So what happened? Okay, so this is why if we look at the continuity formula, there is this dt. Okay, so we have a time step. So the concept here is for a hydrologic system, the amount of water stored as stored or storage may relate to the rates of inflow and outflow. Okay, so here we have ds, the change in storage relates to the inflow and outflow, I minus q. So here we can use the integral equation of continuity. So integral here means ds over dt, the change of storage against the change of time. So we can get the inflow rate. The inflow minus the outflow rate. So it is actually the change of storage. Okay, so because it involves time step, so it will have a time interval. Okay, so the continuity equation may be written in terms of average inflow and outflow. Okay, ada bar atas ni, so it means average inflow and outflow. So here, okay, so we may write it this way. Okay, let me change the color. The integral, okay, the change of storage against the change of time. So we can estimate by using the average of inflow minus the average of outflow. Okay, and then we uh, can just simplify here. O means outflow. Okay, Q is flow. All are flow actually. I is inflow and O is outflow. Okay, here is another way of explaining using some graphs here. So we have inflow hydrograph and we have outflow hydrograph. So if to say we plot both at the same graph, okay, so we can see its relationship. So here, referring to figure inflow and outflow hydrograph, the area between the inflow and outflow hydrographs for a given time interval. So the given time interval is here. So we can, the area between the inflow and outflow hydrographs for a given time interval represents the change in storage volume. So where is this area? So it is here. Okay, I make a shade here, this yellow shade. So this is the area between the inflow and outflow hydrograph. So this is the change of storage. Yeah, you see here? Yeah. So this area, small area here. Oops, forgive my sengit. So here is the area. So this is the change in storage volume. Okay, the inflow, if the average inflow is greater than the average outflow during this difference in time, the change in storage will be positive. Yeah, it means they will. It means the outflow is lower. Okay, so that is what we want actually. So the effect of this storage here, the effect of this storage in decreasing the peak flow. Here we can see it decreased the outflow peak and broadening the time base of the hydrograph is called attenuation. Okay, so for computation, we actually use this basic continuity equation. So I hope you remember this. This is the change of storage, S2 minus S1. So what is 2 and 1? 2 here is actually the time step. Time step. 1 means the first time step. 2 means the second time step. If you have 3, 4, 5, so that is the third time step, fourth time step. So for here example, the first and second time step. Okay, so here we have the change of storage on the left hand side and the change, the difference between the inflow, the average inflow and the average outflow. So here what we know, remember that I told you for routing we need to have the inflow information. So that means that we know I1 and I2. Okay, we know all the I1, I2, I3, I4, I5, all the time we know what is the inflow value. And then we know the first S1, the first storage volume, the beginning of the calculation, we know the storage, okay? But we need to calculate, okay, we need to solve the storage of the next time step, the second time step, and the outflow of the next or second time step. So what we know is S1, I1, and I2. What we want to solve is S2 and O2, okay? Okay, so we will recall back the basic equations or relationships here. So hydrologic routing is actually based on combining the equation with a relationship between storage and discharge. And for storage outflow or level pool routing, the approach is based on the premise storage and it's a unique function of outflow. Outflow is the discharge going out from reservoirs, okay, but we need to know the inflow data, okay. But for Muskingum routing, okay, which is used for channel routing. Here it calls here for streams and river. It relates storage to a linear function of weighted inflow and outflow. So we know both. We know inflow and outflow. So there will be some weighted linear function of weighted inflow and outflow to determine the storage value. Okay, remember difference from the reservoir routing is actually we know the inflow data. Okay, so we will determine the outflow data, okay, and the storage. We can reorganize the basic equations to like this. So we put all that we know on the right side here, known. Okay, I put here known. So we know I1, we know I2, we know S1. Okay, and we can assume O1 first as the first time step. And we want to compute this S2 and O2 here. This is the left hand side. So we want to compute S2 and O2. Okay, so this is the routing algorithm. Okay, so we will also use this information. It also will reorganize the formula. So the next time step, we will adopt this. You might not see this yet. You will see it when we do some example. So we will adopt this, okay, as the next time step. And we also need this relationship, okay, the relationship between storage and outflow. Okay, so this green box, okay, should be determined first. So how do we determine this? It depends on the outflow hydraulic structures of the reservoir. Okay, that is why it is put here to develop this formula, not formula, this relationship. It differ between reservoirs, so it depends on the hydraulic structures, whether it is using a pipe as the outflow or using a weir, what kind of weir for the outflow, or does it use the spillway for the outflow. So this, it differs. Okay, the relationship differs. Okay, so the time step, we might also use this kind of formula. It's actually the same basic formula, but just the arrangement, the rearrangements of the formula. So you might not see this yet, but when we do the example, you can see the relationship here. What does this slide means? Okay, this is what I told you about the hydraulic structure. So the type of hydraulic structure to for the flow to go out from the reservoir. So this relates to the outflow and the storage. Okay, so it depends on the hydraulic structure. Remember the storage outflow relationship, the green box before. So this is the, for example, if we have a spillway, so this is the relationship between O is the outflow and H is the head. So head actually means uh, there is some additional head where the flow starts to go out from the reservoir. So this head means that level. Okay, that level when the flow of water starts to go out from the reservoir. So this formula depends on different type of hydraulic structures. Okay. Okay, so we need to identify this first. Discharge, sorry, the storage and the outflow. Okay, this is the storage in terms of storage and outflow versus the outflow data. Okay, so what does this mean? Is actually we need to make like this kind of graph. So x-axis is the outflow and y-axis is the storage information. Okay, to S over difference in T plus O. Oops, plus O. Okay, so we can say this is a storage versus outflow. relationship. So we need to create this graph first. Okay, the next question is how do we know what is our difference in time? Okay, actually we don't know. We can choose any interval. Okay, we can choose any interval, but there is a guideline. We may use it approximately between 20% to 40% of the in this case they put 9 hours, so it means of the time of peak. Okay, so for this example, given a triangular inflow hydrograph. Why is this triangular? There is a method. Okay, this is like a design inflow hydrograph. We don't have observation data, but we can estimate the inflow hydrograph. So here, that's why it's the shape is like this, a triangular inflow hydrograph. This is like a design hydrograph, so it becomes a triangular shape. So let's say we know the Q peak is 9 hours, so we can estimate or we can try using for the difference in time, we can use between this range 20% to 40% of the peak, the time hour of during the peak. So it's 9 hours, so between 1 hour to 3.6 hour. So for example, to ease calculation, we may use the difference in time as in this case 2 hour, because it falls in the range between 1.8 to 3.6. Alright, so here is a summary of the algorithm. Okay, it's quite a mess before, I know, too many formulas. So this is a summary of the algorithm. So step 1, you need to prepare the reservoir level versus storage relationship using the water surface elevation versus area information. So what is this? This can be obtained. I mean, the elevation versus area information, it can be obtained from topographic map of reservoir. Okay, so you have this. There will be an explanation on what is elevation versus area, and then so we from this. Okay, sorry, I need to jot down here. From the elevation versus area information, we will get the level versus storage. Yeah? So the step 1 is to determine the level versus storage information. Okay, step 2. Okay, so first we have this level versus storage information using elevation versus area information using this formula. Okay. And step 2 is obtain the storage versus outflow. Okay, storage versus outflow in the form of like this formula. Okay, so it will be in the form of this storage versus outflow. So it will be in the form of like a graph. Okay, you will need this. Yeah, there will be a graph with the relationship between the storage versus outflow. Okay, so how do we do this is from the step 1 information, from the level versus storage identified from step 1, and the discharge outflow versus head. Okay, so the discharge outflow versus head, so this is what, if you remember, it depends on the hydraulic structures of the reservoir. Okay, what kind of structure used to for the flow to exit the reservoir. Okay? So it depends on the type of outflow structure. Okay, so step 2 is actually we get this number 2, storage versus outflow, this one, the graph. And then step 3, you do the flow routing. So this is where we will do there will be a table, and then you will do some calculation based on some algorithm which will be explained later. Okay, so I will try to explain a little again using some figures. So step 1, again, you want to find the level versus storage relationship. Okay, so there is some formula for that, and how do you identify this relationship is from the topographic. Okay, the topographic, the elevation information, the information of the volume of this water and the water level in unit depth. Okay, storage and water level. So topographic means the bottom, so you know the elevation, So when you know the elevation from the topographic, you know the water level depths. Yeah? So and then you can calculate the volume of this whole body of water. So that is step 1, level versus storage. And then step 2, you want to determine the storage versus outflow. So outflow here, okay. I hope you understand this figure. What is this? This is a reservoir. So this is the structure, okay, used to detain the water. It's a dam, okay, a structure. It can be a dam, it can be anything. It can be a wall here, okay. It can be a detention pond, as long as it's a reservoir. So for reservoir, a dam, or a detention pond, so you will need a outflow, right? Like a hydraulic structure for the flow of water to go out. Okay, so that is what we call outflow. So for step 2 is we want to find the relationship between here the storage and the outflow. Okay, the storage, the volume versus outflow. Okay, so this one, remember, we use some kind of like a graph, okay, to represent the relationship. And then when you get these two, or actually when you get the storage versus outflow, and you use together with the basic continuity equation, then you can do step 3. Okay, so step 3 involves storage versus outflow relationship from step 2, and it involves the continuity equation that was explained before. Okay, so this is used to actually determine the outflow. Okay, what is the hydrograph? Okay, what is the hydrograph? For example, here there will be another stream here. So this graph, okay, so this hydrograph here, okay, this is some kind of flow outside here. So this hydrograph, okay. Okay, so we go to example. Okay, I hope it will make you more clear here. So what information do we need? Okay, we have a dam. Okay, so that is a reservoir. So we use reservoir routing, and we have a this uncontrolled weir spillway. Okay, so this is the hydraulic structure I mentioned. So this reservoir uses a weir spillway, okay, to make the flow go out from the reservoir. So it gives some description. It has a 10-meter wide with a crest elevation of 548 meter. What is a crest elevation? Means the I will try to draw a little here. So wait, okay. So we have like a wall of the dam. So the water will be here. Okay, this is the water, and then this is the ground level. So the water should be able to go out, right? So here we have a spillway. So let's say this is the spillway. So what does it mean by a crest of elevation of 548? So it means the crest is the top of this spillway is 548. Okay, or usually spillway is maybe underneath here, maybe. Okay, I will erase this part. Okay, so the spillway means the crest of the spillway might be this. So there will have some opening here. There is an opening here. So the crest of the spillway is 548 meter. This means that at the elevation of 548 meter, let's say this there is an elevation here 548 meter, 548. So once the water level reaches 548 meter, then the water what will happen? The flow can go out. So this is what it means, the crest elevation of 548 meter. It means that once the water level reaches 548 meter, it means that the flow can go out from this reservoir. Okay, and then there is another information here, discharge coefficient of 0.45. So this is actually used for determine the relationship of the outflow, okay, and the head. Okay. So there is some discharge coefficient. I think it's CD, maybe CD 0.45. So it depends on the hydraulic structure. So you want to know this coefficient to determine what is the outflow, or if you have a certain head. So head is, for example, you know that 548 meter, once the water level reaches 548 meter, it will flow out. So head means above 548 meter. Okay, for above 548 meter, like this, maybe there will be some additional head here. So 2 meter, for example. So at 450 here, there will be a head of 2 meter here. Okay. Okay, and then the reservoir water surface elevation versus area relationship provided. Okay, so they already provided step 1. Okay, oh no, not yet, you need to estimate step 1 using this information: reservoir water surface elevation versus area relationship. Okay, you want to get this so that you have the storage versus elevation relationship. Okay, next, the inflow hydrograph provided in the table is to be routed through reservoir. Okay, so they give you the information of the inflow hydrograph. Remember, for if you want to do reservoir routing, you have to have an inflow data. So they give you the inflow data. And then here, use the starting surface elevation in the reservoir as for a 544 meter. And then they also give you the difference in time. They already give you the difference in time. You don't need to estimate anything. They give you directly the difference in time as 1 hour. Okay, so what do they give here? Use the starting surface at 544. So because it's a water level in the reservoir, so you have to have some kind of starting point. So here it puts 544. Okay, so this is an example of a real image of a dam. So where is the, okay, so it will impound water here, and you need to know what kind of structure, okay, the water go out. Yeah, so it might be this one, or here, I'm not sure. What about this dam? So you need to identify what kind of hydraulic structures used to flow the water out from the reservoir. Okay, and then what else? Yeah, so the water, okay, so this is what we call the topographic information, where we, from this topographic, and we know the ground level of this. So we can estimate if a certain level of water, let's say here is, I don't know, 100 meter, 100 meter too a lot. No, it's okay. 100 meter maybe. The level of water in that dam is 100 meter. So what is the volume of water being impounded? Okay, so that is what we call the elevation and storage relationship. Okay, so going back to the example before, so I showed you some example of a dam. So it might be used to imagine the structure for the example before, example 1. So they said uses the um, spillway, yeah, weir type spillway. So that is the structure to flow the water out. Okay, so here is the storage capacity information that we can estimate from the area elevation curve. So they gave you the area elevation curve. So for each elevation here, this is the elevation. Let's say we have 1, 2, 3, 4, 5 elevation lines. So for each elevation, okay, we know the area. Okay, so the above image here, this is the elevation, okay, and this is the area for each elevation. Okay, how do I explain more here? Okay, for example, this, what color should I use? This, okay, this small, okay, this line, this is the elevation of, let's say elevation 1. So the area of the elevation 1 is this one. So this is the area of the elevation 1. Okay, and then another color, this is elevation 2. Okay, so the area of elevation 2 is here. Okay, the whole thing here. So that is the elevation of the the area of elevation 2. So why do we need this information? Because we want to calculate the volume of water. What is the volume? What is the volume at elevation 1? Okay, what is the volume at elevation 2? What is the volume at elevation 3? What is the volume at elevation 4? Okay, and what is the volume at elevation 5? So we have the area information, so we can estimate the volume information. So we can use this for determining the storage and elevation information. Okay, so this is the data they give you. Water surface versus area. Water surface elevation versus area. So DH would be 532 minus 530. So DH is 2. 2 meter. 2 meter is DH. And then we get the area for each elevation. So then we can calculate the volume, the storage. Okay, and then they also give you the inflow data. So this is the inflow data. This is the inflow data. This is the elevation versus area data. So going back, so this is step 1. Okay, so step 1 is how do we determine the storage versus elevation. So here we can use this formula. So we can use this formula. Okay, so it's actually let's say, okay, maybe I will explain in the next figure. Okay, so for example, S1 is the storage here. Wait. S1 is this storage. Okay, this storage. So S1, okay, because it starts with 1 here, so Si would be 0. Okay. So 0 is 0. So bawahnya. So 0 is here. Okay, like here. This is 0. Tak ada. And then so S1 is area 1. So this area 1. Okay, area 1. This is area 1 plus area 0. So this is 0. Okay, so this means that actually this area multiply by dH over 2. Okay, so dH is this one. Okay, this is dH for the first volume. Okay, the first volume. So dH over 2. So it's actually taking like an average. Okay, the volume, because it's not a simple like a square shape, right? It's like this shape. Oops, the shape is not square. Okay, it have like a slope, so that's why they use divide by 2. Okay, so you get the first volume here. So you get the first volume, you get the first level. Okay, H, and then you continue for the next okay, this volume. Okay, you want the whole volume actually. So that's why for elevation number 2, you need to add the storage 1. Okay, so for S2, storage level number 2, this is 2, this is 2, 1, okay, 1, 2, 3, 4, 5. Okay, so for S2, you need to add S1. Okay, S2 equals to S1 plus A2 plus A1. A2 plus A1. So A2, okay, the whole here, the whole thing here. A2 plus A1. This A2 plus A1, okay, and then multiply by DH. So again, DH is here. Okay, DH will be the same. Okay, DH sela ketinggian. So, and then divide by 2. Okay, why do you divide by 2? Because you want to get the average. Yeah? So then you get the storage of S2. So S2 is all of this. Okay, all of this. And then for S3, so on. So for S3, so for storage S3, this whole thing here, okay, for S3, this whole thing here. So it's S2 plus, okay, S2 is, you already calculated before, so this is S2 plus A1 plus A3 plus A2, okay, like here, okay, so it becomes A3, 1, 2, 3, so this whole thing, this whole area, okay, plus A2, okay. Okay, and then multiply by DH and divide by 2. So then you will get the storage for S, the whole S3. So that is the concept. So they already give you the area, what is area 1, area 2, okay, what is area 1, what is area 2, okay, what is area 3. So then you can calculate, okay, you can get the relationship. Okay, before we go on, just a simple explanation here. So this is a reservoir. So this is spillway. Okay, this is spillway. So there will be like a crest level. Remember, certain crest level, the flow will go out from the reservoir. So the crest level is like maybe this. Mana ni, right? So crest level. Okay. So anything above this crest level, there will be a head. Remember head. You have a head, there will be of course it will flow out. Okay, if it's higher than the crest, then there will be a head and the water will flow out from the reservoir. So this is just a simple information on the what a reservoir have. Okay, some active storage, dead storage, active storage, normal pool level, surcharge storage, maximum pool level, and the spillway. Yeah, here is the spillway. Okay, so the crest of spillway is, where is it? Here. Okay, this is the crest of spillway. Any flow of water, okay, higher, any elevation, sorry, any elevation, water elevation higher than the crest level, okay, so the water will go out. Okay, so this is what we call step 2. So we want to identify the discharge, no, the outflow versus storage information. So we need to have this information first. Okay, the discharge, we need to have this information: discharge or outflow and head relationship. So depending on the hydraulic structure, so for example for spillway, this is the formula. So remember we have CD, okay, 0.45, okay, it's mentioned in the example. And then we have head. Okay, so head is the difference of level of the water level, okay, against the crest of the spillway. Let's say this is the crest of spillway, and then you have a water level here. Okay, so head is, where is head? Bukan kepala. So head is here. Okay, so this is head. The difference between the level of water level and the crest of the spillway. Okay, so now you want to find the outflow based on the the outflow and elevation relationship. So you have to use the hydraulic structures formula. So in this case, because it's a spillway, so we use this formula. Okay, O equals to 19.9 Hg over 2. So what is head? What is H? What is this H? So remember, once the water is higher, I mean the elevation, the water level, the elevation is higher than the crest elevation, then you will get a head, okay, because the water is higher than the crest elevation here. So for example, if the elevation of water is 550, so it's already it's higher than the crest elevation. So if you minus these two, 550 minus 548, you will get 2 meter. Okay, so 2 meter is the head, and then you can get the outflow. Okay, so the outflow is 56 using the this formula. Okay, and then the next is 552. So 552 is the elevation. So what is the head? So the head is, you need to minus 552 minus 548. So you will get the head as 4. So use the this formula, okay, and then you will get 159 meter as meter cube, okay, per second, which is the outflow, and then so on. So this relates the elevation of the water relates to the head, and then it relates to the outflow. Okay, so for step 2, you can use this kind of table. So for example, this relates everything. This relates step 1 and step 2. So remember, step 1, we get the where is it? The elevation versus storage. Okay, so we get this from step 1, and then for step 2, we want to get the you want to get the storage versus outflow. So using the formula before. Let's say we know that the crest level of the spillway, because it uses a spillway, we know it's 548. So we calculated from the previous slide for elevation of 550, so we get the head as 2 meter. And then using the formula of the hydraulic structure, so you get the 56 meter cube per second for the outflow, and then so on. 552 minus 548, you get 4, and then use the formula, you get 159 millimeter cube per second for the outflow. Okay, so how do you combine step 1 and step 2 here? Is because you want to get the storage versus outflow. So now if you put everything in the same table, so you will get the information or relationship between storage and outflow. Alright, the next step is you have to get the storage versus outflow information in this form. Okay, that's why you need the storage versus outflow first, and then you can convert this storage into this form, 2s over difference of time. In this case, the difference of time, it was given to use as 1 hour, and then plus outflow O. So just use this formula to calculate column 6 here. Okay, to calculate all these values. Just use the storage information and the outflow information. So why do we want to have this form? Okay, because we want to use it for the flow routing. So remember, for step 3, we will do the routing, the flow routing. So we will use this form of formula. We use this form, and then we will use the continuity equation. So that will be on the next slide. Before going to step 3, this is just an example how the calculations are made, so you can check this. Okay, but remember, you need to make sure use the right unit. Okay, this is 2s storage, so make sure you use the right unit. So because meter cube per second, okay, so storage should be in meter cube, and this storage should be in meter cube, and this difference in time should be second, because our outflow is meter cube per second. So please be aware of the unit. Okay, the unit should be right. The unit, okay, the unit should be right. Okay, so using those values, okay, you have determined. So you need to plot the graph. This storage, okay, this storage versus the outflow. So y-axis is the storage, and the x-axis is the outflow. So you will get this kind of line. So if you get this line to ease your calculation for the routing, you can extract the line formula, the line equation. You can get like y equals to mx plus c. So you can extract this line formula so that you can put into your calculation more easier. Okay, so this is step 3, which is how do we do the flow routing. So for step 3, we have another steps, 5 steps here. So how do you do it? Okay, before we go on to these steps, I will just show you mentioned. So for this step 3, you need to make this kind of table. So column 1 until column 6. So what do we know? What do we know is column 1 and column 2 here. We already know this. It is given. Remember, we need to have an inflow data first to do the flow routing. So this is given. The inflow data is given with a time interval duration as 1 hour. See, 1, 2, 3, 4, 5, 6. So the time interval is 1 hour here. And then the inflow data is given. So the next step is you can calculate the values of column 3. So just column 3 just add I1 plus I2 means the first time step plus the second time step. So you get the value for column 3. So you finish calculate all the values in column 3 first before you continue the steps, the next steps here. Okay, so I will clean this up. Okay, so now we move on. So now we need to do the steps. Okay, so step 1. So the first step is you assume the value, the initial value of outflow, which is in column 6. Okay, in column 6 here. So you need to assume first the first initial value as 0. Okay, so this is 0. So and then step 2, determine value in column 5. So next you move on to here. Okay, you move on to column 5. So how do you calculate this? Is you use the graph of storage versus outflow curve. Okay, so you might use the graph, or you might use the formula generated from the graph. So for here example, if the outflow is 0, so from the graph you get the 2s over dt plus outflow as 101 113. Okay, next you can move on. Now you want to calculate column 4. So for column 4, this is where we use the continuity equation here. So just you need to follow this formula. So for column 4, 2s over dt minus outflow. Okay, here it's the same. Okay, 2s minus dt minus outflow. So how do you calculate? It is you use this information here. I mean this formula here. Okay, so where do this formula comes from? Okay, so for example, 2s over dt plus o. So this is column 5. See, this is column 5. And then minus 2 multiplied by outflow. So this is outflow from column 6. So just for column 4 here, you just need to multiply value from column 5 minus 2 multiplied by values in column 6. Okay, so how do you derive this formula? You should look back in the theory, the basic theory. You can find it in the previous slides before. Okay, so now you have value of first you get value for column 6, and then column 5, and then column 4. Okay, so you have these values already. I will clean this up for you. Okay, so you have column 6, column 5, and column 4 for the first time step. Okay, the first row, it means this is the first time step, the first row. So you want to move on to the next time step. Okay, time 1. Okay, before was time 0. So you want to move on to the next time step. So how do you do that? Is you move on to step 4. Okay, determine a value in column 5. Okay, determine value in column 5 for the next time step. So the next time step, you want to determine this value. Okay, so how do you do that? by adding column 3 and column 4. Okay, add column 3, okay, and column 4 of the previous time step. Okay, this is what we call the continuity equation. So I will highlight you here. Okay, this is what we call the continuity equation. Okay, this is what we call the continuity equation. It relates the previous time step to the next time step. So that is why it is called continuity equation. It relates previous time step to the next time step. So in this case, determine value column 5, 2, 1, 3 here. Okay, I will erase some things to make it more clear. Okay, so for the next time step, we are moving to the next time step. We start with column 5. So how do we calculate this 213 here is you add, okay, column 3, I1 plus I2, okay, see the formula is similar, plus the value of column 4 at the previous time step. Okay, this is what we call continuity equation. We add column 3 plus column 4 of the previous time step to get column 5, 213. Okay, and then you move on to column 6 here. So how do you calculate this column 6 is you use the storage flow relationship again. Use the graph in the previous slide. Okay, use the storage versus outflow curve again, okay, to get the column 6. Okay, so now you already have the values of column 5 and column 6 for the next time step. So what do you do next is you repeat step 3. Okay, you repeat step 3. Here is step 3 again. Here is step 3. So you repeat step 3 to calculate column 4. Okay, you repeat step 3 here to calculate column 4. How do you do it? By calculating value in column 5. Okay, remember column 5 minus 2 multiplied by column 6. So then you get the column 4. Okay, remember you minus this one. Okay, how do you get column at column 4? The values at column 4 is you minus column 5 minus 2 multiplied by column 6. So you get your column 4 again. Okay, and then you repeat your steps from step 3. You repeat again step 4, determine value in column 5 at the next step. Okay, because you already got all the values for the second time step. Now you move on to getting the values for the next time step, where you will start with column 5. Okay, start with column 5 again using adding, okay, column 3, okay, plus column 4 from the previous time step. So that is continuity. So then you do these steps until you get the whole values for your outflow. Okay, so again, to finish it, just repeat step 3 until step 5. Okay, until you calculate everything. Okay, so here are a more detailed step-by-step calculations of that previous table. So you can see here it describes more, so you can read it. It's exactly the same as what I mentioned. Okay, until you finish. Again, repeat. Okay, from step 3 until step 4. So you finish part 2. So that is for reservoir routing.